Now we are going to discuss storm drainage, which is essential part of an urban infrastructure. Let us begin with surface drains or stormwater drains. The point says that surface drains are used to carry sewage, which is kitchen wastewater, rainwater. So these drains are mainly designed to remove excess water from roads, streets, and open areas. Now the next point is surface drains are less hygienic since they open and exposed to the atmosphere. This means they can emit unpleasant smell. They may attract insects. They are prone to contamination. The next point is surface drains are normally laid along either side of the street, facing the boundary walls of houses and buildings. So, if you observe urban roads, you will see drains running along both the sides. These collect rainwater from the road surface. Next, in surface drain, it is difficult to maintain self-cleansing velocity. This is because flow is irregular, flow may not be sufficient, water flow varies with the rainfall. So, frequent cleaning is required. Next, surface drains flow under gravity. No pumping is required. Now, let us look at the requirements for efficient surface drain. The inner surface should be smooth so that it reduces the friction. It should have sufficient carrying capacity which avoids the flooding. Then next, it should be proper slopes which ensures the self-cleansing velocity. The joint should be properly finished so that it avoids the leakage. The structure should be stable which ensures the durability. The material should be non-corrosive and resistant to erosion. Finally, the slide shows the shapes of the surface drains. The common shapes include rectangular, trapezoidal, semicircular, U-section, and the V-section. Each shape is selected based on flow capacity, construction cost, and the site conditions. Now, let us move to storm runoff estimation. Determining the quantity of sewage from a community is essential for designing systems such as collection, pumping, treatment, and disposal. Now, the total wastewater includes sanitary sewage, stormwater flow, and groundwater infiltration. This is very important because the wastewater is divided into two parts. One is the dry weather flow and next one is the storm weather flow. The dry weather flow refers to wastewater flow during periods without rainfall. So this includes domestic sewage and industrial wastewater. It does not include the stormwater. The consequences of flow apply to combined sewer system and separate sanitary sewer system. Now, dry weather flow mainly consists of domestic sewage and industrial wastewater. It is also called as sanitary sewage. The formula is dry weather flow is equal to population into the rate of water supply. This is very simple and widely used formula. Now, let us discuss the factors affecting the dry weather flow. The factors affecting dry weather flow includes rate of water supply, population growth, type of area served, and infiltration of the groundwater as well as exfiltration. Now, let us focus on the rate of water supply. The rate of water supply is expressed in liters per capita per day. Now, the important observation is the quantity of wastewater entering sewers is less than the total water supply because some water is lost due to domestic consumption, evaporation, lawn sprinkling, industrial use, firefighting, and leakage. Also, infiltration from subsoil water may increases the flow. Now, a key design assumption, water entering sewers is approximately equal to water supply minus the losses. In many cases, wastewater flow is assumed equal to water supply for simplicity. Finally, the sewer should be designed for a maximum of 150 liters per capita per day. This is a standard design value. Now let us understand the effect of population growth. The quantity of sanitary sewage directly depends on the population. As population increases, water demand increases, sewage generation also increases. Now the formula is the Q is equal to rate of supply in water supply into population. So future population must be considered in design in this formula. Next, the type of area served. The quantity of sewage depends on whether the area is residential, industrial, or commercial. In residential area, sewage depends upon water supply and the population. In industrial areas, sewage depends on the type of industry. Different industries produce different quantities and different types of wastewater. So surveys are required to collect the accurate data. Now let us discuss infiltration of the groundwater. The groundwater may enter sewers through leaky joints and the cracks. This increases the flow in the sewer. Now the exfiltration. This is the reverse process. It means sewage leaks from sewer into surrounding soil. This leads to the pollution of groundwater. The important point here is both infiltration and exfiltration are undesirable. The infiltration increases the load on treatment plant, whereas the exfiltration causes the environmental pollution. So, sewer joints must be properly sealed and it should be watertight. This ensures efficient functioning as well as the environmental protection. In this slide, we are going to discuss a concept, factors affecting the wet weather flow. The first and the most important factor is the intensity and the duration of rainfall. The intensity refers to how heavy the rainfall is, usually measured in millimeters per hour. The duration refers to how long the rainfall lasts. If the rainfall is high in intensity, water falls faster than it can infiltrate into the soil, leading to more runoff. Similarly, if rainfall continues for a long duration, even low intensity rain can saturate the soil, eventually increasing the runoff. So, both high intensity and long duration significantly increases the stormwater flow. For example, A short heavy rain may cause flash flooding, while a long continuous rain can lead to widespread flooding. The next factor is the area of the catchment. A catchment area is a region from which rainfall water is collected and drained to a common outlet. For larger catchment area, the more rainfall will be collected and that will have higher stormwater flow. Whereas the smaller catchment area will have the less runoff. Simply put that, bigger the area, the more water it contributes to the drainage system. Another important factor is that slope and shape of the catchment. The steeper slopes allows water to flow quickly, reducing infiltration and increasing the runoff. The gentle slopes slow down the flow, allowing more water to infiltrate. The shape is also the important factor playing the role here. A compact catchment produces faster and higher peak flow, whereas an elongated catchment spreads the flow over time, reducing the peak discharge. Therefore, slope and shape directly influences both the speed and volume of stormwater flow. Now we consider the nature of the soil, which includes permeability, vegetation, and the built-up area. Permeability determines how much water can infiltrate. Now, if you have that sandy soils which have high permeability, it will result in the less runoff. If you have the clayey soil, which is the low permeability, it will generate the more runoff. Vegetation also helps absorb and reduces the flow. The built-up areas like cities with concrete structures prevent the infiltration and increases the runoff significantly. This is why urban flooding is more common than the rural flooding. This type of pavement also plays an important role in generating the runoff. Impervious pavements like asphalt and concrete do not allow water to pass through, leading to high runoff, whereas the permeable pavements allow some infiltration, reducing the stormwater flow. Modern urban planning encourages permeable pavements to reduce the flooding. Another key factor is that initial moisture content in the soil. If the soil is already wet or saturated, it cannot absorb more water, leading to higher runoff. If the soil is dry, it can absorb more water initially, which results in the reducing the runoff. For example, rainfall after several rainy days causes more flooding compared to rainfall after a dry period. Climatic conditions like humidity, wind, velocity, and temperature also affect the stormwater flow. High temperature increases evaporation, reducing the runoff. Wind can influence rainfall distribution, and humidity can affect the evaporation rates. Though these factors have a smaller impact compared to rainfall on soil, they still influences the overall water balance. Finally, the number and size of available of drainage channels also plays a crucial role. More and large drainage channels will have better drainage and reduces the flooding. And fewer or smaller drainage will have channels will have poor drainage will increases the water accumulation. So proper drainage infrastructure is essential for effective stormwater management. We are going to discuss how to determine the quantity of stormwater flow, which is very important aspect in the design of drainage systems, sewers and flood control structures. Whenever rainfall occurs, a portion of water flows as runoff. Estimating this runoff accurately helps engineers design safe and efficient stormwater systems. There are two main methods used to determine the stormwater flow. The first is the rational method and next one is the empirical formula. Among these, rational method is the most commonly used method for small catchment areas, especially in urban drainage basin. So we now mainly focus on the rational method. The rational method is a simple and widely used formula to estimate the peak stormwater runoff. So it relates the runoff of considering the three important parameters: catchment area, rainfall intensity, and the surface characteristics. Now let us look at the formula. Q is equal to AIR divided by 360, where Q is the stormwater flow rate. Here, Q represents the stormwater flow rate, which is usually expressed in cubic meters per second. This is the final value we want to calculate, and it indicates how much water is flowing through the drainage system during rainfall. Next, A represents the catchment area, which is measured in hectares. The catchment area is the total land area from which rainfall water is collected and drained to a specific outlet. In practice, this area is determined using town maps, layout plans, and the satellite images. These maps show features like streets, buildings, playgrounds, and drainage systems. Larger catchment area means more water collection, leading to higher runoff. The term R represents the intensity of rainfall, usually expressed in millimeters per hour. Rainfall intensity is obtained from the meteorological data or rainfall records. Higher rainfall intensity means more water falling in short time, which increases runoff significantly. For example, heavy rainfall in a short duration can cause sudden flooding. Now, one of the most important parameter is I, which is referred to as the impermeability parameter or also called the runoff coefficient. This factor represents the portion of rainfall that becomes a runoff. If the surface is impervious, like concrete or asphalt, most of the water becomes runoff, which will have a higher value of I. If the surface is pervious, like soils or vegetations, more the water infiltrates, so lower value of the I value. So the value of I depends on the land use. The urban areas will have high impermeability value, where rural or vegetated areas will have the low I value. In simple terms, it indicates the percentage of rainwater that flows over the surface instead of infiltrating into the ground. The catchment area served by a stormwater sewage is determined from the maps that show streets, houses, open spaces, and existing drainage lines. By analyzing these features, engineers can accurately estimate how much area contributes runoff to a particular drainage point. To summarize the impermeability factor, it is the ratio of runoff to the total rainfall. If the ground is highly impervious, like in cities, more runoff occurs. If the ground is natural and vegetated, the less runoff occurs here. These factors plays a crucial role in determining the accuracy of the stormwater flow estimation. To conclude this, the rational method is a simple and effective way to estimate the stormwater flow. It depends upon the three main parameters. One is the catchment area, next is the rainfall intensity, and next one is the impermeability factor. Understanding these parameters helps engineers design the efficient drainage systems and also preventing the flooding there. We are going to focus on the two critical parameters used in the hydrological calculations, especially for urban drainage design. That is the average impermeability factor and the intensity of the rainfall. As we know that a natural catchment or a watershed is rarely uniform, it consists of different types of surfaces. For example, concrete roads, asphalt parking lots, grassy lawns, tiled roofs, and gravel pathways also. Each of the surfaces has different ability to allow the water to infiltrate. The infiltrating ability is quantified by the impermeability factor, often denoted as I. A perfectly impervious surface like solid concrete has an I value close to 1. The meaning is 100% of the rainfall becomes runoff. A permeable surface like a garden might have an I value which is as low as 0.1 to 0.2. Now, to find out the overall behavior of that entire catchment, we cannot just take a simple average. We need a weighted average. Let me explain the formula which you see on the slide. Let's say A1, A2, A3 represents the area of different surfaces, whereas I1, I2, I3 represents their respective impermeability factors. Now, we calculate the total impermeable area of the catchment. This is done by multiplying each area by its impermeability factor and summing them all up. That is summation of A times the I. Next, we calculate the total catchment area by summing all the individual areas. That is summation of A. Finally, the average impermeability factor is simply given as average impermeability factor is the summation of the A into I divided by the summation of the A. In simpler terms, divide the total impermeable area by the total catchment area. This is a crucial value. It tells us on average what fraction of any rainfall will turn into immediate runoff across the entire site. Engineers use this to estimate the peak flood flows and design the stormwater drains. Now let us move to the second part, that is the intensity of rainfall. The second major factor in runoff calculation is R, that is the intensity of the rainfall. R is usually expressed in millimeters per hour or centimeters per hour. However, the key point here is rainfall intensity is not a fixed number. It depends on two things. The first one is the frequency. How often a storm of this severity is likely to occur. Example, once in 10 years or once in 50 years. The next one is the duration. How long the storm lasts. For design purposes, we often assume the storm duration equals the time of concentration. The time it takes for water to flow from the farthest point to the catchment to the outlet. It shows a general formula that engineers which we use, especially when local data is limited. That is, Ri is equal to 25.4 into A divided by T plus B. That is, Ri is the rainfall intensity in mm per hour, whereas T is the duration of the storm in minutes. Again, typically the time of concentration. A and B are the constants that depends on the region and the storm duration. You will notice that here, referencing recommendations from the United States Ministry of Health here, it suggests that the constants A and B taken one set of values if the storm duration is between 5 to 20 minutes and another set of duration of 20 to 100 minutes. The difference is due to that because short intense storms behave differently from less intense ones. The constant help calibrate the formula to real world storm patterns. Next is the time of concentration. This is critical because it directly influences the design of culverts, storm drains, and other hydraulic structures. So let us go through it thoroughly. Look at the definition of the slide. The longest time without unreasonable delay that will be required for a drop of water to flow from the furthest point of the drainage area to the point of concentration. Imagine you have a catchment area that is on the hillside, a neighborhood, or a parking lot. Somewhere in that area, there is a point where all the water collects. It may be a drain inlet, a stream crossing, or the downstream end of a culvert. We call these points as the point of concentration. Now, imagine a single raindrop falling at the farthest possible location in that catchment. The point that is most difficult for water to reach the outlet. The raindrop must travel over land through gutters along small channels and finally reach the point of concentration. The time of concentration, which is often denoted as TC, it is the total time that raindrops takes to make the entire journey. Why do we say without unreasonable delay? Because in nature, water might get trapped or soaked into the ground. But for engineering design, we assume a reasonable continuous flow path. We don't account for unnatural delays like water being absorbed by a dry crack or in a depression forever, which is staying in a depression. In other words, TC is also the time required for the flood discharge to reach its maximum limit at the outlet. Because once the raindrop from the farthest point arrives, the entire catchment is contributing to the runoff. Before that moment, only the part of the catchment is draining. After TC, that is, flow becomes constant for a steady rainfall. The time of concentration is not a single simple number. It is made of two important distinct parts. That is the formula is TC is equal to TE plus TF. Let me define that each component. The first TE is the time of entry. This is also called as inlet time or overland flow time. The time of entry is the time it takes for the raindrop to travel from the furthest point over the ground surface until it first enters a defined drainage system, like a roadside gutter, a storm drain inlet, or a small channel. During this phase, the water is flowing as sheet flow or shallow concentrated flow. It moves across lawns, pavements, parking lots, or the agricultural fields. This is a part of the journey is usually slow because the surface is rough and the water depth is very shallow. When we look into the factors affecting the TE, we have surface slope. That is, we have the very steeper slope where there is faster flow of water will happens. The next one is the surface runoff. Here, the concrete is smoother than the grass, so it moves very faster. The next one is the length of overland flow path. So we can observe that the factors affecting the TE includes surface flow, surface runoff, as well as the length of the overland flow path. Next, we are moving into the time of flow that it is denoted by here the TF. This is also referred to as the channel flow time or conduit flow time also. Once the water enters into the drainage systems, a storm drain pipe, whether it is a storm drain pipe, an open channel, or a small stream, the time of flow will begins. This is the time required for the water to travel within the drainage system from the inlet all the way to the final point of concentration. This phase is generally faster than the overland flow because the water is concentrated in a defined path which has a greater depth and encounters the less resistance relative to its velocity. So the factors affecting the TF includes channel shape and size, channel slope, roughness of the channel lining, and the presence of vents, junctions, and the obstructions. Why do we need this split into two parts? The reason is in engineering design, we often use different methods to calculate each component. The time of entry and is usually estimated using empirical formula that consider land use, slope, and surface type. For example, a grassy residential area have longer TE values than the paved parking lots. The time of flow, TF, is calculated using hydraulic formulas like Manning's equation because the water is flowing in a defined channel or the pipe. By adding them together, we get a realistic time of concentration. Let me give you a quick example. Suppose you are designing a storm drain for a small housing complex. TE, a raindrop falls on the farthest corner on a lawn. It takes 8 minutes to flow over the grass across a driveway and reaches the inlet. Whereas the TF, once inside an inlet, the water flows through a pipe system. It takes 7 minutes to travel through the pipes to the final outlet point. Then TC will be given by 8 minutes plus 7 minutes equal to 15 minutes. That 15 minutes is the time after which the entire catchment is contributing the runoff. In the rational methods, which we have discussed earlier, this TC is used as the storm duration for calculating the peak flow. We move to a topic, hydraulic flow in sanitary sewers. This topic helps us understand how sewage flows through sewer pipes and how we can design the system effectively. Let us begin with the factors that influence the flow of sewage in sewers. The first factor is slope of sewer. Slope is very important because sewage generally flows under gravity. A steeper slope increases velocity, while a flatter slope may lead to sedimentation and blockage. The second factor is geometry of sewer. This refers to the shape and size of the sewer pipe. Circular pipes are most common, but their diameter plays a key role in determining the flow capacity. Next is roughness of the interior surface of the sewer. If the pipe surface is rough, friction increases, also flow velocity decreases. If it is smooth, flow is more efficient. Next, we look into the vents, transition, and obstructions. These create turbulence and energy losses, reducing the flow efficiency. Then we have flow conditions also. This includes whether the flow is laminar or turbulent, also full flow or partial flow. Finally, we will look into the characteristics of the sewage. Sewage contains solids, organic matter, and chemicals. These affects the viscosity, density, and the flow behavior. Now let us move to the hydraulic formula. The first is the Chassis formula. The Chassis formula is V is equal to C to the whole square root of 4s, where V is the velocity of flow and S is the hydraulic gradient, or we can refer to the slope. R is the hydraulic mean radius, which is given by R is equal to A divided by the P, in which A is the cross-sectional area and P is the wetted perimeter, where C is the Chassis constant. Also, the discharge is given by Q is equal to A into V. So, this formula helps us to calculate velocity and discharge in open channel flow like sewers. Next, we move into the Kutter's formula. Now, Chassis constant C is not fixed. It depends upon the roughness. Kutter developed a formula to calculate the C more accurately. Here, N is the roughness coefficient. When N decreases, pipe is smoother. Large diameter pipes generally have lower roughness effect. This formula is useful in open channel and sewer design. Next, we look into the basins formula. Another way to calculate Chassis constant is using the basins formula. Here, K depends upon the nature of the inner surface. So, both Kutter's and basins formula help improve the accuracy of the Chassis equation. Now, let us continue with more hydraulic formula used in the sewer design. Manning's formula. This is one of the most widely used formulas. The velocity is given by V is equal to 1 divided by 1, R to the power 2 by 3, S to the power 1 by 2, where N is Manning's roughness coefficient, R is hydraulic mean radius, and S is the slope. This formula is very popular because it is simple. Also, it gives the reliable results. It is used for natural channels, man-made channels, as also for the sewer pipes. It accounts for real-world conditions like which has roughness and the slope. The next we are moving into the crimp and Birch formulas. This is a modified Manning's formula in which V is equal to 83.5 R to the power 2 by 3 and S to the power 1 by 2. This assumes that 1 by N is equal to 83.5, or we can directly take as N is equal to 0.012. This is specifically used for designing velocities in open channel sewers, hydraulic engineering of sewer systems. For a circular pipe, simplified forms of discharge equations are always used. This formula makes calculations easier when standard roughness values are assumed. Next, we are moving into the William-Hazen's formula. This formula is used for flow under pressure, especially in the water supply pipes. The William-Hazen's formula is V is equal to 0.85 C R to the power 0.63 S to the power 0.54, where C depends upon the pipe material. For example, smooth pipes have higher C value, whereas rough pipes will have the lower C value. This formula is used for water supply systems, irrigation networks, and fire protection systems. It helps us to calculate the velocity and the frictional head loss. Now, we move into an important topic, which is sewer design. Let us begin with the introduction of sewer design. Sewers are pipelines that convey wastewater from households, industries, and commercial establishments to treatment plants or disposal points. So, in simple terms, sewers are the backbone of any sanitation system. They ensure that wastewater is safely transported away from living areas to prevent the pollutions and health hazards, also environmental degradation. Now, proper design is very important. Proper design ensures effective removal of sewage, avoidance of health hazards, prevention of sewer blockages and overflow. If the sewer is not properly designed, solids may settle, pipes may clog, also overflow may occur, and disease spread may increase. Now let us look at the type of sewers. First is the sanitary sewers. These carry only domestic and industrial wastewater. Second is the storm sewers. They convey the rainwater. The third one is the combined sewers. These carry both sanitary sewage and the stormwater. Next, sewers can also be classified based upon the flow type. The first one is the gravity sewer, second one is the pressure sewers, and the third one is the vacuum sewers. Now let us move to the design considerations. One important difference is between the water supply pipes and the sewer pipes. In sewer pipes, sewage contains both organic and inorganic solids. These solids tend to settle down and clog the pipe. Sewage may cause wearing of the pipe materials also. Therefore, sewer pipes must be designed with proper size and gradient to ensure non-silting velocity and non-scoring velocity. This ensures the efficient and safe operation. Now, let us continue with the design consideration. Self-cleansing velocity. This is also very important in the design considerations. The self-cleansing velocity is the velocity at which both floating and heavy solids are transported and sedimentation is avoided. If velocity is too low, the solids settle, also the blockage occurs. If velocity is too high, pipe may get eroded. Now, it depends upon the size of the sewer. The larger the sewer, the higher the velocity required. Next is the minimum velocity. The minimum velocity to avoid silting is equal to the self-cleansing velocity. It is generally taken as 0.75 meter per second. So, this is a standard design value used in the practice. Next is the Manning's formula. This formula is generally used to design the sewers. It gives the mean velocity of flow based on the slope and size of the pipe. So it is very useful for hydraulic design. Next is the flow conditions. When flow is more than half full, the velocity becomes equal to or greater than the full flow velocity. This is a very interesting hydraulic behavior. Next, we are moving into the maximum velocity. Maximum velocity occurs when the depth is above 0.81 times the full depth. Also, the minimum diameter of sewer should not be less than 150 mm. This ensures proper flow and ease of maintenance. Now, let us move on to the circular sewers running full. This is a very simplest case. The pipe is completely filled with water. Now let us understand the parameters. That is, first is the area of the cross section. In that area of the cross section, which is denoted by A, which A is equal to pi d square divided by 4, where d is the diameter. Wetted perimeter is given by P is equal to pi d. This is a portion of pipe in contact with the water. Then is the hydraulic mean depth, which can also be referred to as hydraulic mean radius. Here, R is equal to A divided by P. Substituting these values, we will get R is equal to D by 4. So, for a circular pipe running full, hydraulic radius is equal to D divided by 4. This is very important result used in the design. Now, let us consider a more practical case. Sievers usually do not run full all the time. They run partially full. So, let T is equal to depth of flow. That theta can be taken as a central angle, and A is the area, P is the wetted perimeter, R is the hydraulic mean depth, V is equal to velocity. Now, in this case, geometry becomes very complex. Flow area depends on the angle theta. The wetted perimeter also changes. So, we use geometric relations involving sine and cosine functions to determine these values. This analysis helps us understand how flow behaves under varying depths. Now let us go deeper into the calculation. The first is the depth and partial flow. Depth is related to diameter and angle theta. We derive proportional depth using trigonometric relations. That is, second is that area of cross section. Area depends on theta and is derived using sector geometry. We calculate proportional area compared to the full flow. The next is that wetted perimeter. Wetted perimeter is given by P is equal to pi d into theta divided by 360. So it depends on the angle theta. The next is the hydraulic mean depth. Hydraulic radius is R is equal to A divided by P. This also varies with the theta. So all parameters, that is area, perimeter, hydraulic radius, changes with the depth. This makes analysis more complex, but it is a realistic. Now, let us discuss velocity and discharge in partially full slivers. The velocity of the flow using the Manning's formula, we get the velocity usually depends on hydraulic radius and the slope. The Manning's formula already we had discussed in the earlier slides. So, if roughness coefficient does not vary with the velocity ratio can be calculated here using this formulas also. That is, we will be give the proportionate velocity by small v divided by the capital V is equal to small r divided by the capital R to the whole to the power 2 by 3. Now, next we are moving into the discharge. The discharge is given by Q is equal to A into B. The discharge depends on both area and the velocity. Now, we have some observations. When n does not vary with depth, velocity in partially full flow may exceed full flow velocity. So, the maximum velocity occurs at 0.81 times the full depth. Above 12.5% greater than the full flow velocity. The maximum discharge does not occur at the full depth. It occurs at about 0.95 times the full depth, about 7% greater than full flow discharge. These are very important results for the design. So we can conclude from this, understanding the partially full flow is essential because sievers rarely operate at full capacity and design must consider varying flow conditions. Thank you. The remaining topics we will discuss in the next session.